Okay, this is Matter and Measurement, Lesson 5, and today we're going to talk about the difference between accuracy and precision, and we're going to talk about how we determine the number of significant digits in a value. I don't think we're going to get to adding, subtracting, and multiplying, dividing. We'll save that for our next lesson. So what is the difference between accuracy and precision? Well, accuracy is how exact we are, the closeness to a desired value. So let's pick a color here. Let's see. Closeness to a desired value. For example, hitting the bullseye when I'm aiming at it. Precision is how repeatable the results are, or how consistent they are. So when we look at these four diagrams here, these are how well or not so well Cheryl, Cynthia, Carmen, and Cassie did in their archery lesson. Let's start with Carmen because that's the easiest. Carmen was accurate because she hit the bullseye. So Carmen was able to hit the bullseye more than once. So in her case, she was accurate and precise. Let's move to Cassie next over here. Cassie didn't hit the bullseye at all. So she was not accurate. But her results are pretty much clustered in the same area with the exception of this shot right here. So we could say that Cassie was precise but not accurate. Cheryl, on the other hand, all of her shots are all over the place. So Cheryl was neither accurate nor precise. And Cynthia, well, she hit the bullseye kind of once, and then she's kind of got them in the general area. So here's our question. Cheryl, Cynthia, Carmen, Cassie shot the targets above. Match each target with the proper description. Assume that the bullseye is the intended target. So when you look at Carmen, we said that Carmen was accurate and precise. So we'll put Carmen's name here. Now we have precise but not accurate, we said was Cassie. Neither precise nor accurate, we said was Cheryl. And they're saying, I don't know if I agree with that, but Cynthia was accurate because she was close to the desired area, but not precise. She couldn't repeat her results. Okay, moving on. The following data was collected during a lab experiment. The density of the cube should be 10.8 grams per milliliter. Would you say that this data is accurate, precise, neither, or both relative to the accepted value? Well, if it was 10.8, it's definitely not accurate. However, 6.2, 6.3, 6.5 are all in the same range, so we could say that the data is precise. So this data set is precise. It is definitely not accurate. And at this point, I don't know that it would be relative to the accepted value. We'd probably have to investigate why this took place. Maybe some of the samples were mixed up, and what they thought they were measuring was really another substance. I already did that. All right, so let's get to significant figures. Significant figures are a method for handling uncertainty in all measurements. This arises due to the fact that we have different equipment with different abilities to measure accuracy. So significant figures are the uncertain values to the measurement. And sometimes we can refer to them as the estimated values to the experiment. So when we're looking at this ruler and we're examining this mark right here where the arrow is, we know for sure that this object is, well, greater than 2, but less than 3. We also know for sure that this object, because if this is 2 and this is 3, this is 2.5, which means this is 2.6, 2.7, 2.8. So we actually also know that this is greater than 2.8, but less than 2.9. So we know that this arrow is between 2.8 and 2.9. So we know for certain that we can measure to the tenths place, but this ruler will allow us to estimate the length to the hundredths. So we might say that this is 2.85. We can do the same thing when we're looking at a graduated cylinder. Measurements are read from the bottom of the meniscus. Remember, the meniscus is the curvature of the liquid in the graduated cylinder. So we know for certain that this graduated cylinder is greater than 27, but less than 28. So we can, with some degree of accuracy, say that it measures to 27.5 milliliters. So how can we determine the number of significant figures in a number? Well, there's two ways that I'm going to show you. The first way is called the Atlantic-Pacific rule, and the other is just following a set of rules which are pretty easy. You can determine which way works best for you. And the reason why this is called the Atlantic-Pacific rule, because it has to do with looking at a map of the United States and New York being on the right side and California being on the left side. So long as you know that the Pacific Ocean is on the California side and the Atlantic Ocean is on the New York side, you can use this rule. So let's talk about how we do that. I'm going to put some values here. So what the Pacific side means is decimal present. Decimal present, P for Pacific. It means that we start on the left side of the value, find the first non-zero digit, count it, and everything after it. So in your notes you have 0.0019. Decimal is present. I go to the left. I find the first non-zero digit, 1, and count it and everything to the right. So this has 2 sig figs. 65.01. Here we go to the left and we have 4 sig figs. So 6 is our first non-zero digit, and therefore we've got 4 sig figs. The 3 is the first non-zero digit, so you count it and everything to the right, so that would be 3. And in the last example, 700 with a decimal, you go to the left, 7 is the first non-zero, it and everything after it is 3. When the decimal is absent, we use the Atlantic rule. Absent begins with A, Atlantic begins with A. Atlantic is on the right side of the United States. So we're going to start on the right in 80200. There is no decimal present. We find the first non-zero digit, which is 2, count it and everything in front of it. So that's 3 sig figs. In the next example, we have 400,000. There's no decimal. So therefore, we go to the first non-zero digit, everything in front of it, so that's only 1. In 32105, we're starting on the right. The first non-zero digit is 5, count it and everything in front of it, so there's 5 sig figs. And in the last example, 700, no decimal, I start on the right. The 7 is the first non-zero digit, so there's only 1. Okay, so let's look at these. We're going to go through these together. No decimal. Decimal absent, Atlantic rule. I start on the right. First non-zero digit is 7, it and everything in front of it, 3. 3570, no decimal, Atlantic rule, because the decimal is absent. Start on the right. First non-zero is 7, everything in front of it is 3. Here I have a decimal present. Okay, decimal present is Pacific. I start on the left, the first non-zero digit, and everything after it. So 4. Here my decimal is present. I start on the left, the first non-zero digit is 3, it and everything after it is 3. Present again, Pacific, start on the left, first non-zero digit is 3, and everything after it is 3. When we have a number in scientific notation, we're not worried about the exponent. We're just going to look at what we have here. The decimal is present. I count it and everything after it. So that's 4. And in the last one, the decimal is present. I start on the left, the 3, and everything after it is 4. So that's determining sig figs using the Atlantic Pacific rule. You can also determine sig figs just using rules. For example, all non-zero numbers are always significant. So 1 through 9 is always going to be significant. So 1, 2, 3, 4, 5, 6, 7, 8. So I have 9 sig figs here. Here I have 3 sig figs. Zeros located between non-zero numbers are always significant. So this 0 is embedded between 2 numbers. So that's going to be 3 sig figs. Here, I've got zeros embedded between 7 and 9. These are all significant, so this is going to be 5 sig figs. Now, I could also use the Atlantic rule, decimal absent. I'm going to go to the right, count the first non-zero digit, which is 9, and everything in front of it, so it's also 5. Here, the decimal was present. Okay. I go to the left, I find the first non-zero digit, count it, and everything after it, 3. For numbers less than 1, all zeros to the left of the first non-zero number are not significant. So this is less than 1. All these zeros to the left of the first non-zero digit are insignificant, so this is going to be 4 sig figs. I could also use decimal present. I go to the left, find the first non-zero digit, count it, and everything after it, 4. Here, these are basically leading zeros, so there's only 1 sig fig. And using the decimal present rule, I go to the left, find the first non-zero digit, so it's only 1. Zeros at the end of a number and to the right of a decimal are significant. So here, These are significant. It would be 4 sig figs, or decimal present. I go to the left, count the first non-zero and everything after it. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sig figs. I find the first non-zero, count it, and everything after it. Zeros at the end of a whole number may be significant or not. If there's a decimal after the last zero, then they are significant. If there is no decimal, then they are not significant. So this has got 4 sig figs, whereas this only has 1 sig fig. Exact numbers have an infinite number of sig figs. So let's do some practice problems. So here I have decimal absent. So absent is Atlantic rule. I'm going to go to the right, find the first non-zero digit, count it, and everything in front of it. So I have 3 sig figs. Now, if I wanted a rule for this, I would probably do this 5. Zeros at the end of a whole number are not significant because there's no decimal. So this is also rule 5. 1200, decimal absent. I'm going to go to the right, find the first non-zero digit, count it, and everything in front of it. So I have 2 sig figs. This is also rule 5. Decimal present. I'm going to go to the left, find the first non-zero digit, which is 1, count it, and everything after it, which is 4. This is also rule 5 because there's a decimal present, and if the decimal is present, then they are significant. Decimal present, go to the left, first non-zero digit, count it, and everything after it. So this is going to be 6. This is also rule 5 because the decimal's present. 0.001, decimals present. I go to the left, find the first non-zero digit, which is 1, and everything after it. This is only 1 sig fig. Now if we go back to our rules, we're going up to the top where for numbers less than 1, all zeros to the left of the first non-zero number are not significant. So this was rule 3. 10.00, decimal present. I go to the left, count the first non-zero, everything after it, 4. This is also rule 5, decimal is present. This is decimal absent. I go to the right, find the first non-zero. Everything in front of it is 2 sig figs. Here, this is rule 5. There's no decimal. There's probably more than one rule. Decimal is present. So I'm going to go to the left, find the first non-zero digit, and everything after it. So this is 3 sig figs. You can use rule 5 again. 22.101. Well, here we have a 0 between two numbers, plus this is a decimal. So all of this is going to be significant. So we can say rule 5. We can probably also get away with saying rule 2. Oh, and these were also rule 4. Zeros at the end of a decimal point are significant. So 5, 2, we can say that this was also rule 4. This was also rule 4. And let's see the last one, 101,000. So here the decimal is absent. Everything in front of it. So this is going to be 3. And what rule would we use here? Let's see. Probably rule 5 on that one. Okay. I like the Atlantic Pacific rule better because you don't actually have to memorize any rules. You just have to remember decimal present, decimal absent. And that's it for tonight. I will see you tomorrow in class. Have a great night.